Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at the implementation of feature selection methods that we discussed in previous video. So briefly, these were the methods that we looked at from the different uh, sets. So we have variance, univariate based on univariate statistics, recursive, select from model, and sequential feature selection. So we'll try to work on at least one of these from this flowchart. So let's get into Jupyter notebook and start coding. Here I've imported these libraries. So we have NumPy, matplot. Probably don't need. We could try plotting some of the feature importances as to see how they look. So matplotlib, and then we have all these others, including the new feature underscore selection. So let's run this, and these are the versions that I'm working on. And for data, we'll create iris dataset later on. But for now, for some of the examples, we'll use this dataset. And for this, I've already calculated the variance. So let's say the column 1. So let's say this column 1 is feature 1, this is feature 2, feature 3, and then you have these that are on the variances. So we can set the thresholding based on the variances to drop the features. So let's do that in the very uh, first code. Remove features with low variance, and for this we can create a variable select SEL feature underscore selection dot variance threshold, and threshold is equal to, because we know that 0.16 is the smallest lowest threshold, and here we can see that most of the values are just 2, there's just one there. So we can say that if values are less than 0.17, then drop all those values. And here then we can say select sel dot fit fit to x array, and then sel dot transform x. So now as we can see, from the original array we have dropped the first column of 2's, and we just have these remaining 2 columns. So that's low variance. And now let's look at the univariate feature selection. So univariate feature selection, and for this one, first we'll look at SelectKBest. SelectKBest, and this would be for a classification task. So maybe one more hash. Okay. So here we'll use because we are using the for classification. We can select. We need to select the proper scoring method, and for that we'll use f underscore classif. So feature underscore selection dot f underscore class f, and then selection is equal sel is equal to feature underscore selection dot select k best, and score underscore function is equal to f k is equal to 2, and k is equal to 2 means that we need 2 features in the output after they're selected. And to check what are the input parameters for this, we can always look in the help menu, and here we can see this is the score function, and k is the number we can provide to select how many features, and it calculates the scores and calculates the p values as we saw in the previous video. So let's continue, and here then we can fit this. So sel dot fit x and y. So we'll use the same x and y that we have used earlier, and then perform this sel dot transform x. And so in this case now the For x, let's run x. So this is our original data, and from this we dropped the last column based on the score that was found in this method. If you look at ACL.score, I think, okay, let's see how to get the score from this. So run this, get there, and in the help menu, scores. So it's a score with S. So if we go back, SEL.scores underscore. So here we can see that the lowest score was for the third column, and that's why that column was dropped, and the other two columns are still there in the output. And before we move further, let's uh, change this a little bit. Now we'll try to look at the regression. So select K best, and this is for regression. We could just convert the y values to float and see how that works out. So for this, what we need is f is equal to feature underscore selection dot. So for selection, if you remember, we can use the regression. So f underscore regression, and the rest of the code should be the same. So I'm going to copy that, paste here. So then we have SEL is equal to feature underscore selection, SelectKBest, score function is that. We have K2, then select fit on X and transform X. So again, in this case, we get the same output. So here we could change this as type float 32, and so we get the same result. So here you could try using some different types of continuous data and see what type of output you get. Next, let's look at sequential feature for selection. So for that, we'll use the data, which is the iris data set, and we'll look at the classification. So data, and for this we will going to use x comma y is equal to data sets dot load underscore iris, and return x underscore y is equal to true. So here we have four features. So if we look at x dot shape, we have four features, and we'll try to see if we can eliminate unimportant features from these four features. So the first item we'll look at sequential feature selection, and we'll look at forward selection. And for this, we create the classifier that we are going to use. So CLF is equal to linear underscore model dot rich classifier, and then SEL is equal to feature underscore selection dot sequential feature sequential features selector, and CLF n underscore features to select. So how many features do we need in the output? We have 4 total, so let's say we need 3 features in the output, and then we can fit this. So SEL dot fit x and y. So here our y is ones, zeros, and 2. So there are 3 classes, and x would be floats. So yeah, x are the continuous values right there. So let's delete that, and then so when we run this, so that's the fit is done. Now we can look at SEL dot get underscore params, and within this you can get all the information that was within this particular model. And to get specific information about the features, we can look at SEL dot get underscore support, and here we can see these three features were kept and the last feature was the first feature was dropped. So if we look at X, if we look at X, that's how the X looks. So we have 5.1, 3.5, and so on. So let's keep maybe 0 to first 3 rows of that. So that's what we have. Now if we transform it, so SEL dot transform X, and again if we look at just the first 3 rows, then we can see that last 3 were true, so those would be these 3, and those 3 are in the output after the transform is applied, and the first column was dropped. So that's how the forward selection process works. And if we look at the help menu for this, so if we go back here and if I copy this for selector, and we can specify the direction. So in the parameters here, the default direction is forward. So what we can do is copy this, and if we were to perform a backward selection, how would what features would it select? Would that select? So if you type backward, then run this again, run this. We don't need to run this, so let me close that. And so we got that, we have these, so now it says backward, and here again we get the same output. So the first column is dropped, the last 3 columns are retained in the output. Now after this we look at select from model. So let's do that. One select from model, and for this one, okay, so for this we'll use the same iris dataset. We'll create the function, we'll initialize the variable f with this classifier svm dot linear svc, c capital C is equal to 0.01, penalty is equal to L1, and dual is equal to false, and then use that in the select from model. So SCLF is equal to feature underscore selection dot select from model, capital S, F, and M. Then we have that there, and then we can fit this CLF dot fit x comma y and CLF dot transform x. So let's look at the shape. So as you can see, we have just 3 features in the output, and if we were to check what column was eliminated, we can do that. So let's look at the first 3 rows of the original data, which is that. Now if we use the transform feature and look at again the first 3 rows and all the columns, we see that in this case the last column was dropped and the first column is there. So as in the previous method, we saw that the first column was dropped. In this case, the last column was dropped. Now let's look at pipeline, and for pipeline we'll use the same code that we have typed above, so we'll make it easier, which is okay. Let me copy this, just these first 2 lines, and we'll use that in this code right here. So CLF is equal to pipeline with a capital P, and then here within a list we can specify the tuples feature underscore selection, and here I'm going to copy So this entire thing we could also directly paste it here and then copy all of this and then paste that in here. So we have mm, that particular step in the pipeline done. The next one is the actual classification task. So classification, and for this we'll use the rich classifier, linear underscore model dot ridge classifier. And now the pipeline is done. We can now perform the fit clf dot fit x comma y, and here we get a warning, increase the number of iterations. So we could try that. Max underscore iter is equal to 1e3, maybe 1e4. Okay, so this is the fit that we have done. Now we can look at what information is there. We can pull information from the pipeline as well. So for example, we can check the coefficients of the features within the pipeline. For that, we would type, if you type clf.get underscore params, it will give you the entire dictionary with uh, all the key value pairs right here. So for what we are going to do is we are going to use the feature selection. So for this, I'll type feature underscore selection, and then when you run this, you get these, and then from here we can look at estimator underscore c underscore dot coef underscore, and so these are the coefficients. And we can also look at the support values. So clf feature underscore selection and dot get underscore support, and here we can see that the first three features were kept and the last feature was dropped. And we can also check that by running the transform clf feature underscore selection dot transform x, and let's look at just the first first three rows. So here, as you can see, in the x we have x, so 0 to 3 x, we have these columns, and on the transformed matrix we have just the first three. So the last column was dropped, which is denoted here by the false. Now with this, what we can do next is let's try plotting the feature importance on this same data set. Now let's try to plot feature importance. Plot, and for this we'll use, this time we'll use trees, so ExtraTreesClassifier. So we'll import the library from Scikit-learn, import ensemble. Okay, so once we have that, we can now type clf is equal to ensemble dot extra trees classifier, and n estimators, let's say we have maybe 10 trees, and we can type clf dot fit x comma y, and then we can get clf dot, so clf, we can type that in a variable, so maybe feature importance is equal to clf dot feature underscore importances with s fea underscore imp. So those are the feature importances. Now before we create the plot, what we'll do is we need the feature names. So I'm going to load the data set again, data sets dot load underscore iris, and from this we can now get the data dot feature underscore names, and so we have those names, so we can use them. And for the plot, then we have feature importance in this variable. So we'll type plt.bar data dot feature underscore names comma fea underscore imp, and let's run this. So that's the plot. We can change the x, rotate the x text. So x text rotation is equal to 45, and we can also add a label to y-axis, y label, and this is feature importance. So that's the feature importance we get using the extra trees classifier. So that was it for this video. I hope in this video you got an hands-on experience on how to use different methods that are available in Scikit-learn for performing feature selection on a data set. These were the examples that we tried on a toy data sets, but I encourage you to try these on some different types of other real-world data sets and see um, which type of method works on what type of problem, because um, uh, two different methods can give different types of features in the output after selection process is completed. So the criteria for choosing the method for performing the feature selection is also important. In the future videos, we'll combine the material from this information from this videos and also from the ensemble methods to work on a real world project where we will try to predict some interesting uh, prediction values. So until then, please like, share, and subscribe. I hope to see you all in the next video. Until then, thank you.